Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. Hilbert schemes parameterize quotients of a fixed object. In this playlist so far, I've viewed this as a set and I've used ad hoc methods to put a geometry on this set. What I want to do in this video is to show you Grothendieck's method for putting the correct geometry on this set. So unfortunately, there's quite a lot of technical details associated to his method, so I can only give you an informal, non-rigorous treatment of what he did, but the basic ideas are quite interesting and easy to get across. So let's start with some motivation, and we'll fix our setup. So we're going to have some k-linear category C here, and we'll fix some object M inside there. We want to look at quotients of this M, and usually if we look at all quotients we'll get something that's too big. So what we'll do is we'll fix some numerical invariant. I'll call that P, because in Grothendieck's case he was looking at the Hilbert polynomial. What is this? I won't go into what this is. Some of you might have seen this, but it's a generalization of, for example, the k dimension. So if you're looking at, for example, the Hilbert scheme of say n points on the plane, then the numerical invariant that you fix there is that you want the quotients to be n-dimensional vector spaces. So it's just the vector space over the field K, and you just look at the dimension. That's the numerical invariant you want. So in general, you don't just have a single number which gives you that dimension. This generalizes by looking at polynomials. So here, this corresponds to just the constant polynomials, and so it's basically just a single number, and in fact that number will have to be some dimension, so it's a non-negative integer in fact. Okay, but that's good enough. So this one is good enough when you're looking at what are called zero-dimensional subschemes, so points in other words. Okay, so we're looking at the Hilbert scheme, so I'll denote that with H. Okay, and the Hilbert scheme depends on both the M, this object, and also the numerical invariant P, Hilb Pm. This is the Hilbert scheme of quotients Q of M with that fixed numerical invariant P. Okay, so that's a well-defined set. You can have a look at the set, and we want to put a geometry on that set. And what's one of the reasons why we haven't put a geometry on that set? Okay, so one way to think about that is that let's suppose this H here represents what this set is. Basically, I've only got all the points here, this H as a set. This set is meant to be some sort of geometric object. Okay, in the end it will be some sort of a scheme, hence Hilbert scheme, so H. From that point of view, the only thing we've defined is just all the k points of H. Okay, each of these quotients Q corresponds to a k point of H. So another way of thinking about this is you've just defined all the homomorphisms of spec k into H. All the k points of H, it's just all the homomorphisms of spec k into H. Spec k, that's a point, you just map it into there. Okay, so you're looking at the set of all of those. So of course, if you just have this set, there's no geometry defined on the set yet. Okay, so, and there could be lots of different ways of putting a geometry on that set. Okay, so let's try to think about, okay, so what extra data do you need to actually put the geometry on that? Well, the thing is that suppose you're given a variety, or more generally a scheme T. Okay, if you had this geometry on this H, so this is also some sort of a variety or a scheme, then you'll be able to say what is a morphism from that T to H, so from T to H. Okay, not any random function is allowed. Okay, this will be a variety or scheme, so it's more than just the k points on there. Okay, so you should be able to say, okay, if you have the geometry here, what is a morphism from T to H? So the question I want to ask you is, okay, what's a good way of defining this, which is kind of in the spirit of defining the Hilbert scheme by this set of quotients? Okay, I want to do that in a similar spirit. Okay, so this is the way that we'll have it think about this sort of procedure. So firstly, what happens is that, well, if you have a map from T to H, you certainly have a map on all the k points. Okay, so let's pick a k point T inside T. So here's the T inside this T. Okay, so f of T is going to map over to here. This is a k point of H now. And all the k points of H, remember, are just quotients of M. So you get some quotient Q, which depends on this T, QT of M. Okay, so there's your quotient. And in fact, specifying that quotient, QT, essentially tells you where this k point will map to. Okay, so you can do this for each and every single k point of T, right? So that means that at least on the k points, okay, the map from F from T to H is given by this rule, which assigns to every k point T inside this big T, okay, this quotient QT. So you get a family of quotients, okay? So basically, at this point T here, you're going to associate this quotient QT. So you put QT here. And it's a family. So for each point you get this QT. So it could, for example, be a quotient of M, which is some fixed dimension, okay? And then as you vary this point, you'll get a different quotient, possibly, okay? I mean, it could be the constant map, so it could be the same quotient, but possibly different quotients. So you get a family of quotients, okay? So that's just saying what's happening on k points, okay? And the key thing, though, is that you don't want some sort of arbitrary map, okay? And so the thing that you kind of need is, for example, you need in particular this map to be kind of like continuous. So you need to say, oh, well, what should that kind of mean? And this is the key new idea that Grothendieck introduced, okay? So to ensure continuity of this map F, you need this rule, this family, to be nice in a certain way. And the condition that's required here is that QT is flat over T. Now this is an algebro-geometric condition. It also occurs just in commutative algebra. If you haven't seen it before, I'll just have a look at it in the very simple case of where the numerical invariant is just the dimension. But if you want to know the general definition, or you've seen some commutative algebra, you probably know that a flat module is one that when you tensor with that module, that's an exact functor. Okay, so it's kind of nice in that way. And this idea of a flat module, okay, in algebraic geometry corresponds to the fact that it kind of varies smoothly over the base. Okay, so this is kind of one of the things that Grothendieck introduced. Okay, this idea of a flat family. Okay, so let's just have a look at this. So you've got all these quotients, okay, that vary along this T. That's a family of quotients. So what does flatness mean in the very, very special case where the numerical invariant, okay, this P is such that, for example, it says that the k dimension of this QT is equal to D. So what does that mean? So this means that each of these quotients for every single point is a d-dimensional vector space. So you have a family of d-dimensional vector spaces. Okay, and flatness in this case just means that that family of vector spaces is a vector bundle of rank D. Okay, so that's what flatness means. It's a vector bundle, okay? And of course, you should think of a vector bundle as a smoothly or continuously varying family of vector spaces, okay? So that's a vector bundle. And of course, this vector bundle Q, basically, at any point T, close point T, it should give you this QT. So in algebro-geometric notation, we write this as at the point T will be Q tensor over T, K of T. This is the basically the residue field at this point T, okay? Okay, so this is the notation for what is the vector bundle at T, this K point T. This should equal the QT that's in the family. Okay, so you want a vector bundle with this property. Okay. So that's great. So I guess you can use this definition, okay? And so really, if you want to define what are the set of all maps from T to H, okay? We'll call that FMPT, right? Is going to be the set of flat families over T of quotients of this M, such that it has this numerical invariant equal to P. Okay? So that's rather nice, is that now you can talk about not just the set of K points of H, but the set of morphisms from T to H, and these are called, just as the K points are basically homs of spec K into H, the homs of T into the H are called the T points of H. So you can talk about not just the K points of H, but also all the T points for any scheme T. Okay. So that's great. So that should tell you a bit more about geometry. of this H, okay, because it's also telling you how you can map varieties and schemes into here, okay, and you can't just have randomly send points here, okay, in a discontinuous fashion over to H, okay, because you've imposed this flatness condition which prevents that, okay. So how does this help you put an actual geometry on H? And this is rather curious, is that we're going to use a little fact from category theory, actually, which is Yoneda's lemma. So unfortunately, in this board, I can't go through how this works, but if you've seen Yoneda's lemma, this is something that you should know. Suppose now you have any scheme S, okay? It's actually determined by its corresponding functor, the Homs into S. Okay, so in any category, of course, you can talk about the Homs into an object, okay? And that's going to be a contravariant functor, okay? So in this case, you're looking in schemes, okay? So that's a generalization of the category of algebraic varieties, okay? Schemes, okay? And you want to look at all the homomorphisms of a scheme into that S, that fixed S, okay? So of course, that's a Hom set, so you land in sets. And this is actually a functor because, well, you're homing into something. Okay, so that's a functor. And the key point is that basically this functor will distinguish this scheme amongst all the other schemes. Okay, so in other words, if we change this S to a different scheme, a non-isomorphic scheme, okay, well, you'll get a different functor, but it's not just a different functor, it'll be not even naturally isomorphic to this one here. Okay. So this is a way of distinguishing this scheme amongst other ways, and it relies on this categorical approach. It's via the functor. Okay. So the point is that we've got something that kind of looks like that, and here, right, we've kind of defined what are all the morphisms from T to H. It's basically this functor here, right? They're all the morphisms from T to H. So that tells you for each object, for each scheme T here, we've defined what that is, but we haven't defined a functor. So what I want to do is here, I've just defined for each scheme T, this set, okay? So I've defined that something that looks like this functor, but only on the defined on objects. I need to see what happens on morphisms as well. Okay, so I want to lift this FMP T to a functor and a contravariant functor as well. And the way I'll do that is via the notion of the pullback. So you can pull back families, okay? So let me try to explain to you briefly what the pullback of family is. And if you know what a pullback of a vector bundle is, it's basically the same thing, okay? So suppose now you have a morphism of schemes phi from T prime to T. So I've drawn it pictorially here as an example. Here's T prime mapping to T like this, okay? Then we have a pullback. So this is going to be a map. We usually call it phi upper star for pullback. So this is what we're going to do. We're going to make this FMP into a functor now. Okay, this FMP is going to be a functor and it's going to be contravariant. So FMP, we put in this morphism in here, phi, and it goes from FMP of this T to this FMP of this T prime. So it'll take some family Q and it will have the pullback family phi upper star Q. And essentially, it's a generalization of the full pullback of vector bundles. So let me just sort of explain to you briefly how that works if you haven't seen this sort of thing. So essentially, what will happen is if you have a T prime point of T prime, so suppose you have a point inside here. Remember, what you want is you want now a family on here, okay? You've got some family down here, okay? So you've got an element of FMPT, a family Q over this T, okay? And you want a family over here. So what is it above every single point? So that's what we want to say. Suppose you have some T prime mapping to this QT, I mean to this T rather, this little T prime mapping to this little t here, okay? Then what is the value of the family here? Okay, well basically you're just going to make it equal to this QT. So you're going to stick the value of the family at this T prime. You just look at where T prime lands here. This is T, and above here it's QT, so you'll just make it QT there as well. So that's basically what I've written here. Okay, so at this little T prime, what is the value of this family phi upper star Q at that T prime? Well, what you do is you take that T prime, you use this phi there, sorry. It's not an F, it's a phi. You apply phi to this T prime. Okay. And then you look at what is the family Q at that phi of T prime. And that's going to give you this family. And it turns out that this procedure in general, when you pull back flat families, they stay flat. Okay. So that's great. We've upped this FMPT, which basically tells you about not just the K points of this H, but all the T points of this H into a functor. So it looks potentially like this one here. Okay. And so what's the theorem of Grothendieck? Okay, the theorem of Grothendieck is the following. Okay, so suppose you have X as a projective variety, and then M is some sort of coherent sheaf on X. We want to look at quotients of this M. We don't want to look at all the quotients. So there were ones with a fixed Hilbert polynomial P. Okay, so that could be a constant polynomial, which means that you're just looking at quotients, which are just basically of a fixed dimension over the field K. And then we've defined this functor FMP from schemes to set. But by the way, I should just add here that functoriality is important to make sure that there's compatibility in the definitions of all these FMPTs as you vary this T here. Okay, so that's a very, very important thing that the category theory also does for us. Okay, so the point is that we want to say, well, you know, can we put a geometry on this H? Well, the point is that there exists, okay, this functor here is naturally isomorphic to HOMs from schemes into H for some projective scheme H. And that's what we're going to use to define Hilbert PM, okay? So remember by the Yoneda lemma, okay, if you have any other scheme which has this homing into that scheme is naturally isomorphic to this one here, there has to be an isomorphic scheme. Okay, so this is basically the way you use to pin down the geometry on H. One thing that's a little bit unfortunate about this is that it's very hard to actually see what the geometry is. Okay, I'll say a little bit more about how that kind of works out, but in general, the point is that yes, it's very kind of hard to sort of just see directly. Okay, so the construction of this H is quite complicated. Okay, and really used only in theory, and then usually the way you actually show this is true is that you guess what the correct geometry is. Okay, on this H, and you check that when you hom into that H, okay, that functor is naturally isomorphic to this one here. So that's what you usually do, okay? So it's a non-constructive sort of theorem, okay? But it's wonderful because it tells you that, firstly, there is some sort of projective scheme structure on this set of quotients, okay? So that tells you the existence of that, and it tells you that it's kind of uniquely determined, okay? And here it's uniquely termed. I've stated pretty precisely what this is. But in general, actually, the key point is that you have to define not just all the K points, but all the T points. And so you have to be careful about what does it mean to be a flat family of quotients. Okay, so this is a wonderful theorem of Grothendieck's. And I just want to end up by saying a very, very important part of what is this theory involves. Okay, and this is kind of the key point of why Hilbert schemes are kind of useful. Okay, I mentioned this in a previous video in this playlist. That's the notion of a universal family, and I want to show you what's happening here. Okay, so you've got a natural isomorphism between two functors, this FMP and this one here. Okay, inside this functor here, there's a very, very nice object. Okay, so what you can do is you can put for the question mark H in here, and you can look at the identity inside here. That's the identity H inside here. So that'll correspond to a single object or element of FMP of H. So that's a family of quotients over H. a family of quotients over H. So here, the family of quotients, okay, so you're going to look at M, and you look at this over H. So in algebro geometric notation, this is M tens over X. Here's the structure shift O X cross H. That's M. Okay, and you kind of repeat it over H, and you look at the quotient to this U. So that's an element of FMPH. Okay, let's suppose this is the element that corresponds to the identity. Well, then in that case, this is actually the universal family. Okay, so that's rather nice. And how is it a universal family? Well, it's a universal family in the sense that every other family comes from this family. And how does that work? So this is how it works, okay? So suppose now that we're going to look at this functor here, okay? So remember H is this help MP, okay? You're going to look at the T points of it. So Homs from T into here. And this is, of course, naturally isomorphic to FMPT. Okay, so there's an isomorphism there. Okay. So this, remember, this basically is the set parametrizing all the T points of this Hilbert scheme, okay? Or more precisely, it's telling you about all the flat families over T of quotients of M with numerical invariant P. Okay, so there are all those possible families, okay? How do you get them? Okay, so the way you get them is that, well, you take this F here and you just pull back the universal family. When the universal family lives on this Hilbert scheme, and you pull it back to T, and that's going to be the element that you have there. So in that sense, this is a universal family, okay? Any sort of family that you have that's flat family of quotients, okay? That's going to be in one of these, okay? If it's over T, then it's in this FMPT. And you can get it from the universal family just by this pullback. Okay? And so this is a very, very sort of key idea of what's involved. And of course, the way you can do this is that, well, you just work that any morphism comes from pulling back the identity. Okay, it's just composition with the identity. So since the identity corresponds to the universal family, you just pull back. So that's essentially the reason why. But I'll let you think about that if you like. So just to sum up, what have we done today? So this is the key point. If you want to put a geometry on the Hilbert scheme, so the Hilbert scheme, remember, is the set of all quotients of a given object, okay? And you fix some numerical invariants. So we call that H here. So it's easiest to think about this as the set of K points. So it's a set like that. And what Grothendieck said is that, well, if you want to put a geometry on that, you should look at not just the K points, but all the T points as T ranges over all the schemes. And you should think of this as a functor, okay? The functor of T points, the functor of points, okay? And the key thing here is that what should this functor sort of represent, okay? So what should the T points? Well, the T points are basically, so this is something that depends on what your situation is. So I've defined it more or less in the situation that Grothendieck set up, okay? But the key point is that you want families of objects, families of quotients. So I haven't defined that completely precisely here. Families of quotients, and the key sort of condition that you want to add to make sure that you have a nice map is flatness. I hope you enjoyed this adventure in pure mathematics.